In this video, we'll explore the socio-economic component of the CEMPRA toolbox. The socio-economic component of the CEMPRA toolbox is designed to evaluate restoration actions and explore cost-benefit trade-offs across different scenarios. The socio-economic component allows us to understand how different restorations will change our cumulative system capacity scores and stressor levels across locations and restoration actions. The socioeconomic component can be accessed on its own module page called the socioeconomic page. On this page, there's links to the instructions, video tutorials, and an example data set to get started with. The step-by-step walkthrough instructions are also listed to the right of the page. I'll start with the example data set. The first step I'll do is I'll go to the upload data section. Here, I'll upload the stressor response dataset associated with the demo, the stressor magnitude dataset associated with the demo, a locations polygon dataset associated with the demo, and the socioeconomic input workbook that's associated with this demo. The socioeconomic input workbook is a little bit different than the other workbooks we've seen in the previous example. A separate video will be dedicated to going over the input requirements for the socioeconomic input workbook. Once all input workbooks have been uploaded successfully, we're ready to start the socioeconomic module. Pay special attention to any red error messages here. If any appear in the socioeconomic input workbook setting, do not advance forward before resolving them. The Joe model, or the CEMPRA tool in Joe model, functions similarly when the socioeconomic workbook is updated. However, we can see that this tab now becomes active. The purpose of the socioeconomic workbook is to run the Joe model and CEMPRA tool with and without different restoration actions to evaluate different cost-benefit trade-offs. First, I'll run the Joe model just in its own default form. I can see in this example, I have a series of stressors. I'll run the Joe model once, and I'll define a name for the scenario and keep it as default, status quo, or baseline. I'll let the Joe model run as usual. I can see here that the plots below have updated with some of the info for that run. The first plot shows the cumulative system capacity score. The next plot shows the cost. This will make more sense in a 0, but for the default run, it's just 0. And similarly, it shows some of the key stressors. This is the same as the scenario tab in the map interface. However, I'll run the Joe model again, but this time I'll implement the restoration actions through the socioeconomic module to see if any changes take effect. So I'll click the Joe model here after I've made sure that we have the socioeconomic input workbook updated, and then I'll run the module again. However, this time I'm going to change the name from default status quo of the scenario to restoration. I'll also be sure to make sure that this checkbox is checked so the model is run with the socioeconomic inputs enabled. I'll click Run the Joe model, and the model will run again. However, this time I can see the scenario from the previous run and the scenario with the restoration actions enabled. In this example, I can see that this cumulative system capacity score has increased after we ran the model with the restoration actions enabled. I can drill in to see what else is going on. I can see that with this restoration action option, there's a cost that's incurred and an estimate of the cost over the change in cumulative system capacity scores. Each of these dots show the level of stochasticity across all the different batch replicates. Finally, we can take a look at individual stressors in the CEMPRA tool and see how they changed between the default scenario and the scenario with the restoration actions enabled. I can see that most of them stayed pretty much the same. However, there were some increases in the habitat loss and in the August stream temperature. I can also see all the different restoration projects here listed at the bottom of the page. Each project tied to a specific stressor has its own row here. I can go further in and take a look at a specific project and look at details within it. So in this case, I can look at a restoration project proposed for this location that consists of 2 meters of a riparian planting buffer applied to 350 meters of stream length with the intention to improve August stream temperature conditions. I can go ahead and click on the blue edit icon here to open a pop-up that will show all the details about this project. Ideally, what we're looking at here is for an increasing level of restoration action. How far can we move on our stressor response relationship? And are there any inflection points in the cost-benefit trade-offs? We'll come back and look at what these plots mean in just a second here after we look at the data inputs. I can get an example data input here on the main tab. If I just go over to this right panel, there's the video tutorials and then some of the example data inputs. By now, you should be familiar with the stressor response data input, the stressor magnitude data input, but the socioeconomic input workbook is what we're going to go over here. So I can open that up here, and there's quite a bit going on in it in the different tabs, but it's actually, the layout's quite simple once you get the structure of it. So there's a README tab, a management actions tab, and this first management actions tab describes the types of restoration actions, such as beaver dam analog placement, off-channel habitat, riparian buffer of 2 or 10 meters width, and then the measurement unit in which they're going to be characterized, and then the hypothetical cost per unit to implement this type of management action here. Similar to the structure we've seen in some of the other inputs for the tool, it's set up with a mean cost, a standard deviation of the cost per unit, a lower limit, and the upper limit. So each time the simulation is run, it'll resample a different cost estimate for each location, for each action. There's some other codes here to also optionally for advanced uses specify bulk thresholds for discount multipliers. We can see here that just in this dummy example, these values aren't researched from real examples, so they might differ considerably from what you're thinking, but we have an average price per beaver dam analog, an average price on a per square meter basis for off-channel habitat development, and then some average prices for a per kilometer basis of stream channel riparian planting with a skinny buffer and a thick buffer here. The next tab is the location implementation worksheet. The idea of this worksheet is to define an initial estimate of how much of each type of restoration action you want to try to implement at each location. So this worksheet should consist of unique entries between a location or HUC ID and location name and each of the management actions. So at any location, we can implement 1 or more management actions or 0 management actions or restoration actions. But for each row should consist of a unique combination of a location and a management action. The management action names just defined here, the units as well. And then similar to the other previous worksheet, we have a mean number of units that we want to implement, a standard deviation, a lower limit, and an upper limit. So if you knew exactly how many, for instance, beaver dam analogs you wanted to place at a specific location, the standard deviation would be 0. But we allow for stochasticity here to explore the sensitivity in the level of implementation and action. Here, so this is saying 16 beaver dam analogs at tributary A, 2,000 square meters of off-channel habitat development at tributary A as well. And then in this location stream B, we're doing 3,000 square meters of off-channel habitat, and we're planting 100 meters as a linear distance or 0.1 kilometers of a skinny riparian buffer. And then in this tributary A, we're proposing to plant 350 meters or 0.3 kilometers of this particular action. For some advanced cases, there's also a location and cost multiplier. So if for whatever reason you think a specific action at a specific location will be more or less effective than another location or more or less costly, you can use these columns here to make those adjustments. Finally, we have the location size attribute worksheet. So the reason behind the location size attribute worksheet is laid out here if you want to read it. But in the default implementation of the Joe model, we don't have a way to account for the underlying size of a specific location. So if we were to do 100 square meters of off-channel habitat development at a location that consisted of, say, 500 square meters of total stream area, it would have a bigger effect relative to a much larger location that, say, had 1,000 square meters of stream area, and you did the same level or same size of a project. This would have you would increase the stream area by 10%. In this one, it would increase it by 20%, just simply because the location's bigger here. And so that's exactly what this tab is trying to do here. We're introducing location attributes to specify the size of a location so that each of our restoration actions here can be converted to relative densities. So like number of beaver dam analogs per square kilometer of stream planted relative to kilometer of stream, or potentially it could be the quantity of off-channel habitat relative to the stream area or relative to some historic estimate of off-channel habitat. There's some empty placeholders here just to customize this however you would like. The next stressor reduction tab is similar to the main worksheet in the stressor response workbook there. But what this tab is doing is it's linking each of the restoration management actions to one or more stressors from our stressor magnitude file. So this is a little bit of a hokey example, but it's just put together for proof of concept. But in this case, we have two entries for our restoration action of riparian planting, because riparian planting in this case is going to be linked to the stressor of August stream temperature, but it's also linked to our stressor for riparian habitat. Similarly, beaver dam analogs can, in this case, be linked to stream temperature, but they also can reduce habitat loss because you didn't pound water and potentially make stream area. So for each action type, you can potentially improve one or more stressors. So if we looked at our original stressor units, it's an absolute values. So something like beaver dam analogs or large woody debris might be a number of a number of units, whereas something like riparian planting might be measured in kilometers of stream planted. Similarly, off-channel habitat might be measured in meters squared. The next thing we do is from these columns here, we're going to define a location baseline size scaling column. So what we're going to do here is we're going to convert the raw restoration action into a density by dividing the values by the location scaling column. So riparian of stream planted divided by the total kilometers of streams becomes kilometer planted per kilometer of stream. Number of beaver dam analogs per kilometer of stream turns into a linear density. And for off-channel habitat, it could be potentially a ratio of new versus current off-channel habitat. For each of these rows here, each of these stressor reduction functions, similar to the stressor response worksheet, it's the same layout here, but for each of these different stressor reduction curve IDs, we need to define a separate workbook and function that's going to show how this restoration action reduces a specific stressor magnitude variable. So this is the hardest part of the socioeconomic restoration workbook, but the idea is to try to link specific restoration actions to a generalized function that's going to reduce a stressor here. So this is a bit of just a quick example for stressor reduction function 1, which is riparian planting. And it's saying that as we increase the portion of the stream planted from 0% to 100%, we can potentially see a decrease of 2.5 degrees in August stream temperatures. But again, there's going to be a lot of uncertainty around this. So we'll define a large standard deviation and then a large lower and upper limit to say this restoration action might have a large effect or a small effect. But when the model runs, it's going to run with stochastic simulations. And so we want to try to narrow this as much as possible, but this could be a starting point. The next one, we're going to have this riparian habitat indicator variable tied to riparian planting. So the more riparian planting we do, that stressor value is actually going to increase here. Whereas on this one, the stream temperature will decrease from the shading. This is one of the key reasons why we need to convert restoration actions from absolute values to relative densities, is so we can tie these functions together. So we can walk through each of these. Some of them don't have to be as complex. So off-channel habitat can just simply reduce habitat loss. In this case, I've said the off-channel habitat, the more we make of it, we can reduce habitat loss. But potentially you could reduce habitat loss by 80%, but not 100%, because you assume the constructed habitat isn't as good as the original habitat. So that's what's all going on in the socioeconomic restoration workbook. There's extended descriptions in each of these cells. Also, we can refer to the documentation, which we should read before we try to run the socioeconomic module. Okay, so with all that in mind, I can load up the socioeconomic module again. So I'm going to go to the data upload tab. I'm going to load my stressor response workbook. I'll load my stressor magnitude workbook, and I'll load my socioeconomic input workbook. I don't actually need to populate the GIS data for this exercise. So I'll just go straight to the socioeconomic tab. I'll run the model once in this default mode, just to run the Joe model without the restoration actions. Then I'll run it again. I'll change the name of the scenario to something like restoration, and I'll click run with the socioeconomic inputs. So now it'll rerun the Joe model simulations, but it'll apply the restoration actions. I'll click run the Joe model, and again we see this increase in our cumulative system capacity score. We see there's a cost assigned to it, and so on. I can go on and actually, if I had different restoration profiles, I could import other workbooks into here, click run, and call this something like restoration 2, assuming this is another workbook. And then we'd go on and see how the score changes. So each time we run a different workbook, it'll rerun all our calculations again and add it as a new scenario here. Again, we can kind of see how these changes in each of the stressors between the scenarios starts to make sense. So in this case, a lot of them are targeting this August stream temperature. In the default, this system capacity score isn't very good, 57%, but it increases to 62%. Finally, I'll click this button to clear the data from the cache to start over. I can also look at these tables now at the bottom, with all of this information in mind, and it should make a bit more sense now. So if I go to look at this August stream temperature for the riparian planting, I can see here's the level that I'm going to plant. So it's 0.1 and it's in units of kilometers. So this is saying we're going to plant 100 meters linear distance of stream. We say it costs $1,500 per unit. There's 0.1 units and a cost multiplier of 1. So the total cost there would be $150. Obviously, that's probably not super accurate there. And then we can kind of convert that restoration action into a density too. So we're saying this location contains 3.5 kilometers of stream. So 1 divided by 3.5 is a planting sort of ratio of 2.9% or 0.29 kilometers of stream planted per kilometers of stream as a density. What's this going to do to the August stream temperature? So here it's targeting the stressor August stream temperature. We have an initial value of 12 degrees, and we look at this plot. Remember here, this kilometers of stream planted and change in the stream temperature. And we're saying that for the kilometers of stream planted, we're the red dot is the status quo or the do nothing scenario, and the green dot is with the restoration action applied. And so it's saying it's going to decrease the stream temperature by a small amount. The new stressor will be the stream temperature will decrease from 12 degrees to say 11.9 degrees. And then on our stressor response plot, we'll move up the needle a little bit here, and it can show a gain or dollars per percent gain. In this sort of illustrative example too, we can also see a cost benefit plot where it shows the level of action. So how much stream or how much riparian planting are we going to do in units of kilometers on the x-axis? And then this blue line is how costly it's going to be. And the purple line is what's our change in the cumulative system, or what's our cumulative system capacity score or stressor response score going to be? And so there's this kind of inflection point here around 1.5 kilometers there where it shows we have diminishing returns, even though we have increasing costs. So this level here, there's an input box here, which is actually sort of useful, is I can change this value here. And when I change the value of how much restoration action of this certain type I propose to do at this location, all these calculations update, and we can see that we're actually we've moved further out here. We've moved our position from where we started from to where we're going to on the stressor response relationship. And then we've moved out here a bit more. I can go and increase this even more to something really, really large. And it kind of shows we're off the charts here, but we really don't gain any more on our stressor response relationship, or that the way we've characterized this shows it kind of maxes out here. And so we don't move anymore. And then here we're also off the charts. I'll just bring this back to a reasonable value, and then I can save the value here, and then it will update so I can rerun the simulations again with this new restoration action portfolio or profile. I can do the same thing with other restoration actions. So here's looking at a, what was this one, off-channel habitat development at the stream location B. We're proposing to do 3,000. We can kind of look here that maybe we could increase this to something like 30,000 too, and just sort of see how this moves the needle on these plots too. And so we can just kind of keep increasing this and just sort of see where we start to get these cost benefit trade-offs. Finally, when we're happy with all of these, we can go back up and we can rerun the Joe model again, just the default run. And so that in a nutshell is the socioeconomic module. it doesn't necessarily put you in a place for shovels in the ground in terms of restoration projects, but it's a really useful tool for restoration planning for a large area to sort of get some ballpark back of the envelope cost benefit trade-offs going. And then the idea is that this module and this tool will help to kind of seed the conversation and guide some high-level restoration planning into more detailed project designs, which you would do outside of this tool with subject matter experts. But yeah, I hope this can be helpful, and contact us if you have any questions or concerns. Thanks.